We will talk about the complexity of the Gauss elimination and the algorithm of the Gauss elimination in computational programming. Okay, the computational complexity of Gauss elimination. Gauss elimination. Okay, and what is the computational complexity? What is the definition of that? It's basically the total number of operations. And here, when I say operations, it can be multiplication, it can be additions, it can be dividing to get you scale factor for the Gauss elimination. So it's total number of the operations in computational part. And for Gauss elimination, how you measure the complexity of computational power. So think about your Gauss elimination. It's A11 x1 plus A12 x2 plus dot 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 plus A1n xn equals to B1, A21 x2 x1 plus A22 x2 plus dot 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 plus A2n xn equals B2. Then you have dimensional, so an1 x1 plus an2 x2 plus dot 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 ann xn equals to bn. And for the Gauss elimination, basically you are trying to make this coefficient matrices become upper triangular. So the algorithm to doing that, the algorithm for the Gauss elimination will be, so converting to a upper triangular will be for k equals 1, 2, 3 until to n minus 1. Then for another loop for j equals to k plus 1, k plus 2, dot, 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 until n. Each row will do the row operations, will be equals to j minus k times the ajk divided by akk, which is the referred, and. So how we understand this algorithm? What you are trying to do for the first is for the column. So you are trying to make, for example, this column, the coefficient will be all equals to 0, right? This column is 0. The next will be from the A33 downside to be 0 until to the ANN. So for each column, this is represented by column from 1 to n minus 1. You are trying to make each column part will be equals to 0. Well, there is another loop inside this column, which is from j equals to k plus 1, k plus 2 until the n part. You are trying to make, for example, this part to be 0. At the same time, you also need to scan all the rows to make all the row parts refer to the previous row is equals to 0, so that all the later triangular part will be equals to 0. By using this row operation, that the current step, that row will be equals to the current step minus the referring the previous step times the scaling parameter, which is referred to the triangular value. And remember that for each, this part will be many terms inside. So for the column is around n column, for the row is around n row. And for each row, you will need several terms inside. It's around n. So the total worker count number will be around n to the third. So the complexity is around n to the third. And the step 2, of course, the total number will be smaller than n to the third, but this is an estimated number of the computational complexity. Well, for this step 2, you will do the back substitution. So the algorithm will look like, you will first count xn will be bn over xnn, right? The back substitution matrices will look like a11 plus times x1 plus a12 x2 plus a x1n xn equals b1. Then the second term, this part will be 0, will be a2 to x2 plus a2n xn equals b2, a xn equals 2bn. So you can directly get what is the xn from this bn divided by ann. Okay. And then you will do the back substitution using a for loop for x equals n minus 1, n minus 2, until to the front row. Each number will be equals to 1 over ai times bi minus sum of j equals I plus 1 to n aij xj. So that for each row, you will do the sum. For example, if you already know xn to x to 3, then in order to get this x2, sorry, if you already know this xn to x3, you are trying to get this x2, you have to sum all the term here and use b2 minus all the sum here, divide by 1 over a22 to get this x2. So the computational complexity for the back substitution is that for I from n minus 1 to 1 is around n operations. For the sum part, it's around n operations. So the back substitution work count will be around n to the second term. Well, compared to the n to the third, this one is much smaller when your n is much strong. So for the Gauss elimination, complexity is around n to the third. Okay, so it's very computational complexity method to solve the linear system.